Hello and welcome back to Differential Equations, section 5.3, the gallery of solution curves for linear systems. So now we know that we can have any number of equations which would have appropriate number of unknown functions which you are supposed to solve. So our linear system looks like x prime is equal to ax vector, and if you only have one entry, then this problem is your chapter 1 problem, separation of variables, easy, right? But if you have 2, 3, 4 equations and so on, then you have multiple functions, it becomes a linear system, and it's the problem for chapter 4, 5, and 6 and so on. So now when we have a system like this, we said that the solution for that system is your vector v times e to the lambda t. And again, this x is a vector, so that could be just x and a y, or x1, x2, or it could have 15 unknown functions there, whatever. Now remember, this x is not a variable x equals 3. This x is x of t. It's a function of t, because we are no longer in algebra. We now are dealing with, when I write x, I mean x of t. When I write y, I mean y of t, or I mean y of x, which is bad, but whatever. So anytime you see x, right, you know it's x of t, which is a function of t. So all of these here are functions of t, and they are unknown. Now, we have the dimensionality of the system, and dimension is just simply the amount of variables you have. So you will say that square is two-dimensional because it has 2 dimensions, right? The length and the width. And the box is going to have 3 dimensions because it's going to have length, width, and the height. So that's the 3 dimensions. So when I say that we are dealing with a 2-dimensional system, then you just have x and a y, or if you are like x1, x2, right? Whatever. But you only have 2 equations, which means 2 unknown functions. So when the system of dimension n equals 2 means we have 2 equations in the system, which in terms means we have 2 unknown functions, usually xy, or I don't want to write that, usually x of t, y of t, or x1, x2, whatever you want to call them. I mean, you can call them f and g, you can call them whatever you want, it's just 2 of them, because the dimensionality is 2. Now, as soon as you have that, that means that your characteristic equation, so when you have this, that means that your now characteristic equation with the lambda will have 2 eigenvalues with 2 associated eigenvectors. So that's what we have. And now those eigenvalues can have one of the 3 possibilities: 2 distinct real lambdas, or 1 repeated lambda, or complex lambdas. So those are your options. And regarding which one of these you have, there are certain pictures that are associated with this. What do I mean certain pictures? Well, all of the solutions would be some very close iteration of the pictures and drawings that I'm going to draw now as solutions. So for real eigenvalues, which are these are the real, again, we never learned these yet. We don't know how to deal with the repeated ones if you are to say, let's calculate them like we calculated the other ones. So if we have the real ones, they are separated into the world of two distinct or one repeated. Now, they have subcategories. What happens if it's non-zero of opposite sign, both negative, both positive, and then 1, 0, 1 negative, 1, 0, 1 positive. So we have now 5 different cases here, and we have 3 cases here, and we'll see what happens with these ones. Okay, so now let's go and talk about these first. Maybe I should color code these, huh? Yeah, how about we color code these blue, and then we color code these red at the end. So we have black, blue, and red, just to separate them from. There we go. Okay. All right, so let's go with the black ones. When we have distinct real lambdas, we have the 5 cases, and one of those cases is non-zero distinct eigenvalues of opposite sign. So I guess case 1, non-zero distinct. So non-zero distinct real eigenvalues and the of opposite sign, So that's just saying lambda is less than 0 and lambda 2 is more than 0. So that's what we have. And you can also put that together in one, saying lambda 1 is less than 0, less than lambda 2 if you want to, because if you take a look at this, right, and put 0 on the other side, you get this. So whatever. So 1 is positive, 1 is negative. Now, the solutions, if you are to graph this on the plane, where we have x1, x2 axis, there we go. So we are going to have the eigenvectors, and you can set these eigenvectors any way you want. I'll follow the practice v1 and v2 eigenvectors. Now they create these like oblique asymptotes. They create these regions in which we can draw. And now what you have are solution curves that would appear, let's say, in this quadrant here. They appear in this quadrant here. They appear in this. These are not quadrants, these are like the regions, right? So they can be in any one of these. And this is what the solutions will look like. Now observe that your eigenvectors do not curve. And if you remember earlier, last lesson, I said that the eigenvectors are unchanged with the transformation and so on. So that's why they act as asymptotes as absolutes or whatever you want to think of them and call them, the solutions will bend around those vectors, and these vectors will guide them. So now, what we have are solutions where the constants, you remember your C1 and C2 and all of that stuff, because you have that your solution X is given as C1x1 plus C2x2. Now this C1 could be less than 0 or more than 0, and C2 could be less than 0, or C2 could be larger than 0. So the solution will look like this, but the question is which one of the 4 lines do you get to draw? And that is given by if your C1 is bigger than 0 and your C2 is less than 0, then you have this curve all the way to the left to be the solution for your case. So now you just go around and say, right, C less than 0, C2 less than 0, C1 sorry, larger than 0, C2 larger than 0, and opposite, so C1 less than 0 and C2 more than 0. Now, once you solve for your C's, right, you will know which one of these solutions is your curve. Now, all of these could, again, right, change. There was case 1 out of 5 for the first one. So there's a lot of stuff here, and they're all graphical approaches to what you have. Now, your solution here for the distinct negative eigenvalues, which I believe was both negative. Yep, that was the second one. So both negative. So when both eigenvalues are negative, you are going to have sinks and sources. Now, what does that mean? Well, when you draw your, it's hard to draw for me, it's the awkward angle here. Okay, so solutions x1, x2, there we go. Again, put your vectors somewhere. We are going to have points going inside into the point, creating what you would call a sink. So they would drop in and disappear at the point. So the solution will come in and just, boom, go right in. Again, this will create these breakpoints like this. Actually, this one should go more this way. Not that it matters, but OCD. So we go this way, going in again. There we go. And again, it's the game of what the C's are doing. So these ones would be, oh, sorry, this is a sink. Source is when it's come out, when the both are positive. Sinks. Guys, a sink. You know what the kitchen sink is, right? All of the dirty water gets sucked up in that one point in the middle, right? And it goes away. So a sink means that all of these are going into this point in the middle. So when you see the solution, you know it's a sink solution. But when you see the graph, right, you immediately know, oh, both eigenvalues were negative. So you have lambda -2 and lambda -10, for instance. So you don't know what they are, but you know that both of them are negative. So that's what takes care of this. And then you have, again, those, right, C1 positive, C2 negative. Then you flip them over here, C1 negative, C2 positive. The top one are both larger than, and the bottom both are less than. That's always like that. Now, the case is that, right, you will have one of these four, not all four, right, because your C1 cannot be negative and positive at the same time. So it's one of these combinations, right? But you know that both lambdas are negative. So lambda 1 is less than 0, lambda 2 is less than 0, and lambda 1 is not the same as lambda 2. That's also something to say because they are distinct and they're negative. I mean, we are in that distinct group, right? Because everything I draw in black is going to be in distinct group. Then we move to the blue ones and eventually red ones. All right, so now positive lambdas, and those are called source. Now they're like radiate energy out of them. So it's going to be completely opposite picture to what we had here, where you are going to draw the same thing, except now the solutions will be emerging out rather than going in. So your solutions, you know, pick some eigenvectors. And now you are going to have the solutions emerging and going out. So think of it as, you know, the sun shining out with its values, right? Giving the energy out of the sun. So, and again, you have your C1 larger than 0, C2 less than 0. In the top one, both larger, so C1 larger, C2 larger. Over here, C1 less than, C2 greater than, and C1 less than 0, C2 less than 0. Again, though, it's the game of what the constant coefficients are in the front. I mean, the coefficients of those C1, C2. Okay, last two cases for this would be 1, 0, 1 negative eigenvalue. 1, 0, 1 negative lambda. Now, that means did I write over here? No. Lambda 1 positive, lambda 2 positive, lambda 1 different than lambda 2. Again, it's distinct, but let's write it. Why not? Okay, so when 1 is negative and 1 is positive, what you have is again, remember that the negative sucks in, right? So it's like a sink, but it's only one lambda is, they have only one eigenvalue that is a number. The other one is 0. Now, how does that manifest on your picture? Well, when you have your solutions, right? And you pick whatever, again, location you want to pick for your eigenvectors, I don't care. You can pick literally anything. I said that my lambda 1 is 0. Lambda 1 corresponds to a vector v1. So now that one being a 0 is the one that it's going to be attracting solutions. So when you now draw the arrows, right, the solutions pointing one way or another, you are going to get, since lambda 1, right, which is this one is the vector, I'm going to have solutions pointing like that. And again, it's a sink. So everything wants to go towards it. Now, if I chose over here, so let's do it this way. And if I chose, I'm going to draw the same situation. That's a V1, that's a V2. But I chose now lambda 1 less than 0 and lambda 2 equal to 0. Then it would go like this. Because they are approaching the lambda 2 equals 0 is the one that doesn't give any curvature to it. It's just going straight for that value. So, and again, nothing else changes here. I just swapped my lambda 2 to be 0, and that flipped the picture 90 degrees. So there you have it. That's 1, 0, 1 negative. And then we also have 1, 0, 1 positive when it's going to do the same thing, except it's going to go outside. So 1, 0, 1 positive lambda. So if lambda 1 is 0 and lambda 2 is positive, we're going to have the same story, right? You pick you're graphing one solution against the other solution. That's why the axes are labeled as x1 and x2. Guys, it's x1, x2, it's like x and a y or whatever, right? That's technically what you have. But they are all in terms of t, right? Because your x is function of t and your y is function of t. So again, pick any eigenvectors. I like my v1 to be to the left of v2. It doesn't really matter. And now, since I picked a lambda 1 to be 0, that means that's the boss, and everything will be now escaping away from it, right? Because that's that. Now, if you flip this and you put lambda 2 to be 0, then everything will be going away from lambda 2, so the problem would look like that, right? Just 90-degree flip. We got all 5, right? So we have for this distinct roots. You have the ones where you have saddle point, which is 1 positive, 1 negative. Then you have both negative, both for a sink, both positive for a source. And now you have these half links, right? 1 is 0, 1 is negative. That's like half sink, because it's not sinking into a point. It's sinking towards the other vector. And then this kind of half source, right? Which is kind of emerging from the second vector, the one that is positive. So we are done with black cases, and now we're going into blue cases. And the blue cases are repeated ones. So now the repeated ones is, unfortunately, we haven't done repeated yet. So you don't know what the repeated one look like, but you have the proper and improper nodal sources, and then you will have again something for the same thing for the sinks. So when you go with repeated, lambdas, that's when you have that lambda 1 is equal to lambda 2, right? Is equal to just lambda, because the same value. You remember that we had these cases when we did the other things back in chapter 3, right? We had to pre-multiply by x for undetermined coefficients. It was creating a lot of mess. It's creating mess here as well. That's why it's taught all the way back in chapter 5. But we are going to have these graphs now that will have the solutions doing like that, going away. Ah, right? So that's the one way for the repeated. But then when you see, the problem is that we're learning this before we learn. I can't talk too much about it now. When you have the repeated, and then whether you have the vector, eigenvector that repeated or the eigenvector did not repeat, and all of that kind of stuff, we also have the one with the eigenvector right here. This is your vector v. And then you will have one solution go away, right? The other solution again go away like this. But then you will have, and these are now the problem for me to draw. So I'll have to use a different color. There will be another solution going in a direction of the eigenvector. So that's for, right, the sources, and you have the same thing for sinks. Again, we did not learn repeated ones, so this might mean nothing to you until you learn some more of the basics before you can look at the graphs and try to make sense out of this. So we have our eigenvector v, and now we're going to have the solutions. Let's draw solution green. So this one coming in, right, that side, this one coming in right there, and then this one going in, and this one going in, and that's still 4 of them, right? It's just that, again, we have to take a look at all of these cases. And finally, the red ones, the complex ones. When lambda was that p plus minus qi. And why did I do these ones in red? Because these ones are the most times, this is what you get. Mechanical, electrical engineers, and pretty much the other people don't use that much. Anyway, so we have the solution given by the good old C1. A was a cosine qt minus vector b sine qt plus c2. Now this is when it's purely, right, there's no e part. Oh, maybe I should, how about we do this? Just qi. There we go. Because there's no e over here, which means there's no real part to the problem. Okay, let's go. B cosine qt plus a sine qt. There we go. So when there is no real part, right, and you graph these with your eigenvector and everything, you get this sideways ellipse on the graph. It's terrible. That's better. And now we're going to draw this. There we go. Perfect. And these are your directions. So you can, I don't know how far I want to go this, because there's another Euler equivalent formula that can turn back this connect sine and cosine back into the E problem, and the theta, the angle, and then that's the angle of the shift over here. It's like a lot of this stuff that electrical engineers will have to worry about. Mechanical engineers not so much, but electrical engineers will have to worry about this a lot, because they need to make sure that before they flip the generator on, it's in phase with everything else that is on the grid, otherwise it will explode. So especially if you hit the resonance and all of that stuff and make it much worse. So there are a lot of things to consider here, but each one of these, it's like, section is a little bit misplaced because you need to learn everything first and then talk about it. We did not cover those angles and things yet, where you get to take this part here and decompose it into the two vectors A and B, which are the ones that you actually have. So it's kind of very difficult to connect these pictures now to what the actual graphs look like. So I'm just gonna say, yeah, you get an ellipse when it's basic like this. Now, when you get eigenvalue lambda to be e to the pt, when you get the lambda with p plus qi, where p is larger than 0, or should we do less than 0 first? Which one? They did less than 0 first. Okay. Less than 0, then your solution spirals in. So you're going to get like this. So it's spiraling in. And that's because positive one it's killing the energy, so everything collapses in the middle and then it stops. And this is literally what's happening with your pendulum, right? Because it loses energy, and then hits the center and it's dead. And then lambda equals p plus qi, where p is larger than 0. This is where it spirals out. So you have your source, and then it spirals out of there, and it goes outward on the solutions. So we would say spiral sink, and again a source. Maybe could have called it a spiral source. And then you can, move all of this into the 3D. Now, if you turn your page in the book to 315 and 316, you will have this entire thing simplified for you and written all in one spot. And these were exactly the types of graphs. Now I'm dreading that I couldn't find that email fast enough, but unfortunately class is over. If I find it for the next semester, maybe I can ask her to resend me. These were the types of pictures that the graphs posted in the solution. So it's not this is actually used later on, and you know a lot about the system just by looking at the picture. So the hope is that you will. And I think your homework is all about matching these. Yeah, the homework is all about matching these to the equation or solution, whatever. So and on your exam, all you can get for this is like multiple choice questions and so on to kind of match them and match them with the name, match them with the equation, which obviously is a two-edged sword, because there's no partial credit in that case because you're not computing anything. So you either know it or you don't know it. And then, yeah, that's it. So just make sure that you can open the question, i.e. you're not using Mac, because I will have to give you a question in terms of a picture. And if you can't open a picture, then you can't answer the question. All right, so that's a 5.3, a little bit of, pretty pictures. The next section is the second order systems and mechanical applications, where we are going to put a lot of these guys together and, use the method we know to solve a mechanical vibrations problem with a couple of these carts and so on. So it's a second order systems and mechanical applications. So still no electrical until we get to, I think it's 5.6 or 5.7 is where the electrical kicks in again. Because you really need to know a lot of this mess in order to do the electrical. But maybe we can talk about it as well. It is a second order. Anyway, more of this stuff on Monday. So I will see you then. I will remind you of the office hours every day, right? So go on Canvas, pick up the link and a time, and if you have questions, I'll see you there.